So now finally we prove the first main result about representations of a finite group. Remember I showed that every non-zero representation of a finite group G is either irreducible or decomposable. I actually only showed it for finite dimensional representations. It's actually true without that hypothesis. But the theorem I'm going to prove now actually requires that. So G is going to be a finite group, and the statement is that every finite dimensional representation of G is completely reducible, is equivalent to a finite direct sum of irreducible representations. This is sometimes called Maschke's theorem. We've basically done all the work. It's an induction on the dimension of the representation. So we can exclude the zero representation if the dimension is 1. We've seen those are always irreducible. And in general, if the dimension is bigger than 1, either it's irreducible or it's equivalent to a direct sum of two representations, phi1 and phi2. And the key point is that both of these are going to have dimensions strictly smaller than the original representation. So by the inductive argument, these are completely reducible. And therefore the direct sum is. That's it. Let me just remark here. This really does use all the hypotheses, namely that the group is finite, that the representation is finite dimensional, and also that the field, which in our case is the complex numbers, has characteristic 0. Let me just show some examples where things fail. So for instance, here's a representation of the integers. It's a two-dimensional complex representation. I'll send the integer k to the matrix 1, 0, k1. That is not completely reducible. It's not irreducible. It's got an invariant subspace, an interesting one, but it's also not a direct sum. As an exercise, you should try to prove that. A similar example, let's call it phi prime. This will be a representation of zp, where p is prime, in GL2 zp. So this is a representation over the field zp. Phi prime of brackets k, I'll basically use the same formula. Brackets 0, 1, brackets 0, brackets k, brackets 1. That turns out to be a representation, and it's again not completely reducible. Let me note a consequence for matrix representations. If I have a matrix representation over the complex numbers, then there exists an invertible matrix, let's call it P, such that if I take the function phi and conjugate it by P inverse, then I can write it in block form, where there are blocks on the diagonal, which I'll call phi upper 1, phi upper 2, down to phi upper r, and the other blocks are 0, where each of these blocks, phi upper k, defines a representation, a matrix representation of some dimension, which is irreducible. This is just the statement of complete reducibility applied to a matrix representation. The matrix representation will be equivalent to a direct sum of matrix representations. That equivalence is given by a linear map. That's the matrix P. What I'm really doing is choosing a direct sum decomposition of C to the n in terms of invariant subspaces, and then choosing a basis of C to the n which is compatible with those invariant subspaces, so that ultimately I get this block decomposition when I change basis. Make this explicit. Take the standard representation of S3. So here I can take P to be the following matrix. First column is 1, 1, 1. The second column is 1, minus 1, 0. The third column is 0, 1, minus 1. I've talked about these before. I think I call these V, X, and Y. V spanned a one-dimensional invariant subspace, which I called W. X and Y spanned a two-dimensional invariant subspace, which I called U. Both of these actually turned out to be irreducible subrepresentations. Using this P, I can change basis of my representation, and it will have to have the form phi upper 1 and phi upper 2. And then zeros here. So I make this explicit. P inverse phi 1, 2p is going to work out to, I'll have 1, and I'll have minus 1, 0, 1, 1. And then P inverse phi 1, 2, 3p works out 1, and then 0, 1, minus 1, minus 1. It's just a change of basis.